So now that we have been able to come up with the phasor diagram for this AM modulated signal, we would like to derive some necessary parameters and also calculate or come up with the various power requirements of this AM component. So in my previous tutorial, we were able to come up with the general components of the AM wave, and this equation is what we call the envelope, right? The envelope. We have the upper, the maximum sideband and the minimum sideband, right? This is what we call the envelope. So you have to take note that there are some necessary parameters that we can get from this. So based on this phasor diagram that you can see here, and together with the equations, we can see that the amplitude of the lower sideband, which is LSB, let me pick a new pen. We can see that the lower sideband will be having an amplitude to be equal to ACM over 2. The same thing applies to the upper sideband. They also have the same amplitude as you can see over here, which is ACM over 2. That one has been also be verified in the envelope equation, which is this. Looking at it, which is equal to upper sideband, yeah, they all have the same amplitude. Looking at it, we can also calculate the bandwidth of this AM signal. The bandwidth, which is equal to BW, which is equal to upper sideband minus lower sideband. The upper sideband, it's FC. We are using the frequencies instead of omega angular frequency. So the upper sideband is this, and then the lower sideband is FC minus FM, which is equal to B bandwidth. And therefore, what we can do is that when we simplify this, we are going to get bandwidth equal to FC plus FM minus FC plus FM. So this cancel this, we have our bandwidth to be equal to 2FM. So this is the final equation for our bandwidth. When you have an omega, we have bandwidth equal to 2 omega m. But mostly we calculate the bandwidth in terms of frequency, so this is recommended. Let's move on to the power requirements of an AM signal using the envelope equation. So the power requirements. So now we all know that our power in whatever you have been learning, if you're an engineering department, computer science department, I know you all did integrated science in various senior high school, A levels and other side. We all know that power, which is P, is equal to voltage times current. And this voltage is an RMS value, which is V equal to VRMS. And therefore, we can simplify to say that our P equal to VRMS squared over R. This came to play when we are saying that V equal to IR, and we can come to conclusion that I equal to V over R. And when you do the substitution, this is what we are going to get. Since we have an RMS value and then the various amplitude, these are also normal peak values, let me say here, VM, we need to convert the VRMS into a normal peak amplitude. So what we can do is that we know that our VM amplitude equal to VRMS over root 2, and therefore we want to substitute this inside the equation. Our VM here equal to root 2 VRMS, and therefore our VRMS is equal to VM over root 2. So in doing this, we can replace it into the power equation, and when we replace, we are going to get P equal to VM over root 2 all squared over R, and therefore we are going to get VM squared over 2r. Since we have this equation, we can basically go ahead and substitute the amplitude of whatever we have in the envelope equation to calculate for their the respective power requirements. So looking at the double sideband, which is this part of the envelope, it has an amplitude of the carrier's it has a carrier's amplitude, and therefore when we substitute it into this power equation, we are going to get PC representing the double sideband one, going to be get AC squared over 2r. So this is the power requirement for the double sideband. For the power requirement for the lower sideband is the same as the power requirement for the upper sideband, since they all have the same amplitude. And therefore, when we substitute, you know the amplitude is equal to ACM over 2. As you can see in the envelope equation, this is it here. So now that we have this, we can substitute inside ACM over 2 all squared over 2r. And when we do that, we're going to get AC squared m squared over 4 all over 2r. And at the end of the day, PSC B and equal to PSUB should be equal to AC squared m squared over 8r. So this is the various power requirements. So if you are being asked to calculate for the total power requirement of an AM modulated signal, is P total equal to P of the double sideband PC plus the P of the lower sideband plus the P of the upper sideband. And therefore, we can say that our PT to be equal to AC squared over 2r plus AC squared m squared over 8r plus AC squared m squared over 8r. So now that we have this, we can further simplify it to get whatever we want. So in finding a common LCM for this, we are going to get 8r into bracket 2 AC squared m squared plus AC squared over 2r equal to PT. P total power requirement, and then these two cancel this, we are going to get PT equal to AC squared over 2r plus AC squared m squared over 4r. So what we can do right now is that simplifying it further, PT equal to AC squared over 2r into bracket 1 plus A, no, I don't get an A again, AC squared has come out, m squared over 2. So as you can see, this AC squared over 2r represents the PC, which is this one, right? The PC, which is this one. And therefore, we can say that our PT equal to PC into bracket 1 plus m squared over 2. So this is the total power requirement for the AM modulated signal. So if you are being given the power for the carrier signal, and then you are being given the modulation index, you'll be able to calculate the total power requirement of the AM modulated signal. But aside that, you can also be asked to calculate the power requirement for the upper sideband if they say that it is the same as PUSB equal to AC squared m squared over 8r. When you are being asked to calculate the power requirement of both sidebands, then it's both PUSB and then PLSB, and you'll be good to go. When you are being asked to calculate the power requirement for the double sideband, it's AC squared over 2r. So this is the power requirement analysis for AM modulated wave, and then we have also been able to calculate the bandwidth for this AM modulated waves. In one of my video series, we were able to come out with yet I think at the beginning of this tutorial, we came up with this waveform. So in view of this, if we want an AM A max, let's say A max, the maximum amplitude, this is the maximum amplitude because at this point, let's assume that the message amplitude was 5, so it was added to the carrier amplitude AC plus 5, so we got the maximum, right? And then A mean, that one we assume that it was minus 5, so we subtract and we get A mean, right? So now A max here, which is equal to V max, can also be represented by the amplitude of the carrier plus the amplitude of the message. As I was saying, if it's 5, it's added; if it's minus 5, it's subtracted. So A mean can also be equal to AC minus AM. That's what we need to take note. And when we add them, we are going to get A max plus A mean to be equal to 2AC, and this one will cancel this one, and we are going to get AC equal to A mean plus A max. The same thing applies to when you subtract it instead of adding, we are going to get A max equal to AC plus AM, then minus A mean equal to minus AC plus AM. So now this one cancel out, and we are going to get 2AM to be equal to A max minus A mean. Now let's take note of this equation. So since we have AC equal to AM, A max equal to, let's say AC equal to A mean plus A max, and then AM equal to A max minus A mean. let's write them here. I think we get a max space here. So now AC equal to A max plus A mean, AM equal to A max minus A mean. And remember that we were saying something like the modulation index, which is M, and we came to the conclusion that it's AM over AC, and therefore when we replace these ones inside, we are going to get A max minus A mean over A max plus A mean. So you can see that if you are not being given the values of AC and AM, and you are being given the maximum and the minimum amplitude, you'll be able to come up with a modulation index, of which I believe will help you to calculate the total power requirement of an AM modulated signal. So one thing that you have to also note is that whenever the modulated signal index, which is M, is less than 1, it is called under modulation. Under modulation. When M, which is the modulation index, equal to 1, it's equal to critical modulation. And when M is greater than 1, it is called over modulation. So that's one thing that you have to take note of. Now we are done with everything. Keep watching, and I'll see you in my next video.